Hello, my name is Alex Dickinson. I work at the University of Southampton in the UK, and I'm very grateful to the European Society of Biomechanics for giving me the opportunity to provide a perspective talk about the state of the art in simulations supporting prosthetic socket design and some future research directions. When we think about the rehabilitation pathway that somebody goes through after amputation, we often focus on the activities that highly performing people are able to undertake, like returning to work or elite sport, and often we focus on the prosthetic limb itself. There are tens of thousands of euros in a microprocessor controlled ankle like this, which allows it to adjust its stiffness, kinematics and kinetics to walking speed and surface changes. But all of our function depends on the part at the top, the prosthetic socket. Especially in early rehabilitation after amputation, the soft tissues need to heal, stabilize as edema subsides and muscle atrophy causes volume loss, and they undergo extensive functional adaptation to a new load-bearing scenario. The tissues on the distal end of this residual limb or stump are formed from the calf muscles and skin, and initially they're very load intolerant and vulnerable compared to the plantar tissues on the sole of the foot. It's accepted that this rehabilitation process involves considerable discomfort and pain, and it depends on the load transfer between the limb and the socket is made as a work of sculpture by a highly trained prosthetist. Socket design is relatively unchanged in principle since the 1960s. The prosthetist will capture the limb shape by plaster casting, create a positive mold, and then perform manual rectifications where they add and remove material strategically. For example, they might remove material from the mold at the patella tendon, as shown here, so that when they create a check socket by vacuum forming, they'll have a press fit between the socket and the limb in that location, whereas material might be added to the mold at the vulnerable distal tip to create an offloading. The check socket is tested and adjusted, and then finally a definitive socket is produced. CAD/CAM methods developed since the 1980s and now represent approximately half the sockets produced in the UK today. The residual limb external shape is digitized by scanning, rectification is undertaken in software, and then the socket mold is CNC carved by conventional draping, or then some people go direct to 3D printing the sockets. Importantly, however, the techniques are used in a very similar way to plaster casting, by freehand and by experience, despite a vast quantitative data foundation. All this means that the socket design and fitting is very iterative, which comes at a high cost to health services and inconvenience to patients. Prosthetists have been asking for more evidence-based design methods for some time. We as engineers have the motto from Lord Kelvin that if we can't measure it, we can't improve it. Prosthetists want to measure the effects of their skill-based practice and then predict what will work when they design for a new patient. So considering the technologies that might provide some of this evidence, limb socket interface pressure and shear stress sensing is established in the research community, and FEA was proposed to sit alongside CAD back in the 1980s, although the residual limb shape capture technology available was coarse, and clearly computational power for FE model solution was low by today's standards. Several review papers were published in the late 1990s and early 2000s, and they expressed the potential of these technologies and gave scope for their improvement. But despite making these improvements in computational modeling and biomechanical fidelity, when we repeated the review in 2017, the technologies weren't in clinical use, and it's still not the case today. So what's the problem? In fact, we identified several challenges relating to the biomechanical scenario and relating to barriers against clinical implementation. Considering modelling, the problem contains almost all the factors that implicit finite element method struggles with. The soft tissues are highly hyperelastic and their properties change dynamically, and potentially they undergo large deformations. The limb contains a large number of bones, tendons, ligaments and discrete muscle bodies, and these are in contact. And there's also a complex contact condition between the prosthesis and the limb, with the socket donning process producing large sliding distance. External loading is dynamic, and we know there's considerable deviation from normal anatomy in terms of pathology, like scarring and bony spurs, and different surgical approaches. We know the community hadn't truly accommodated variation in these parameters, with the largest study only analysing 5 participants. And all these complexities led to a very non-linear relationship between socket rectification and pressure. Indeed, making the socket smaller at the distal tip might actually prevent distal loading altogether, if the socket can no longer be donned until you get tip-tip contact. From the perspective of clinical translation, we face the disruption of introducing these technologies to very busy clinical practitioners who have established workflows and little time to invest in the inconvenience and risk associated with learning a new technology. With conventional FEA formulations, there will be a high cost of computing equipment, FE software, and the human resources or the engineers needed to create and solve and interpret the models. And this is in addition to the cost of the CAD/CAM equipment required for the design and mold fabrication, which the approach depends upon, and which still are not available across all clinics. If volume imaging is needed as well, MRI scans are not routine in these individuals, and they're only performed when some investigation is required. On top of this, some members of the prosthetics community understandably perceive a threat to their profession and skill from simulation and prediction, or AI tools. And alongside this, we acknowledge that the human clinician is the expert. As shown in the following images, a range of different socket design philosophies are possible, and they'll potentially all work. Here we represent a socket design by registering the limb and socket shapes and by plotting their deviation with an accessible colour map. This patella tendon bearing design strategically loads and unloads particular structures. The total surface bearing design aims for uniform loading and minimal pressure gradients. The KBM design is different again. We imaged the same individual using MRI, wearing all three of these sockets, and the images show how they reconfigure the soft tissues quite differently. And while the KBM didn't suit this individual, the PTB and the TSB were reported to give similar comfort. So there is not necessarily one correct answer. And even more than these challenges, we have great trouble knowing how to interpret the models. In the ESB, we're used to relatively complex failure models for the materials and tissues we study, but this is a step of additional complexity. My researcher Jenny Bramley set out to understand the pressure tolerance of residual limb tissues by understanding their ischemic and inflammatory response to the loads applied using blood pressure cuffs to represent prosthetic loading. She used transcutaneous oxygen and carbon dioxide measurement to track ischemia, inflammatory cytokine biomarkers collected from sweat, and inspected deformation and strain using MR imaging, as well as looking at how the tissue composition changes from an intact to an amputated limb. We could see evidence of biomechanical adaptation in response to the loads in the residual limb tissues compared to a person's contralateral limb control and control limbs of people without amputation. But we could also see how temporary ischemic reactions took place. This is seen by a 100% reduction in transcutaneous oxygen pressure, followed by a subsequent increase in transcutaneous CO2 at far lower loads than are predicted and measured in prosthetic limb use. We also saw that these results were very patient-specific. Therefore, we recognised that any modelling like this would need to take a comparative approach instead of being so basic as setting a single safe pressure level. So working towards FEA methods which might be appropriate for clinical use, we had to identify how complicated a model is complicated enough, and we had to come up with strategies to minimise the computational expense. I set my researcher Josh Steer the challenge of developing a pipeline for implementation which would be feasible using a low-performance NHS laptop. We wanted to consider how this might be useful for any new patient visiting a clinic and to consider the effects of population variability. And this is an extra challenge in populations like this, where pathology increases variation beyond that which just comes from basic anatomy, and where we have considerable surgical variation superimposed. So we built a statistical shape model using principal component analysis upon a group of 80 residual limb cast surface scans collected at Portsmouth Enablement Centre. Now looking at these casts, you can see large, medium and small sizes, and you can see conical through to bulbous shapes. But the PCA approach allows us to capture these main trends in variation quantitatively using a small number of parameterized dimensions. And then we can identify and measure finer features that aren't so obvious. So we generate a mean shape, and on top of that, here we can see how you can distinguish variation in residual limb length from variation in the soft tissue profile from conical to bulbous, abduction adduction changes, and then more discrete local rectifications like the ones that I described earlier. Now, because we'd identified that comparative modelling was the approach to take, this allowed us to reduce the level of complexity and use a simpler model in terms of the soft tissue structures that are represented. We also reduced the computational expense by parameterization. So we fully parameterized the baseline model in terms of the socket design rectification map, and we used the parameterized anatomic and surgical variability from our statistical shape model with a radial basis function, a mesh morphing process, so that we could describe the whole population shapes with a comparable finite element mesh. Finally, we constructed a Kriging surrogate model so that with pre-computation we could enable a much faster lookup, if you like, of finite element results for variations in socket design or limb shape. Josh improved this further for high-speed lookup of results in a graphical user interface using the same PCA approach to produce a statistical output model. So this is the result, where a prosthetist can drag sliders to change the socket design parameters and receive a real-time update to their pressure predictions, including all the complexity of socket donning and external loading. We could replace an optimized more than 30-minute finite element analysis solution with an MRI scan, image processing, an Abacus license, a desktop computer and an engineer into something that would deliver a result within 2 milliseconds on a web app with less than 3 kilopascals or 5% error in our prediction of the interface pressure. For example, you can see quite clearly the effects of changing the patella tendon feature here, as well as more subtle effects of scaling and other rectifications. And although we have to admit it's still not yet in widespread clinical use, Josh did secure enterprise fellowship funding from the Royal Academy of Engineering to work towards translating this into the clinic. As an aside, and certainly not useful clinically, we did undertake a validation study, recognizing that all the clinically available experimental measures of stress are confined to the interface between the prosthetic socket and the limb, or to the device itself, and that control conditions are unavailable. We produced a replica residual limb model for an MRI scan using sawbones, silicon and sand particles mixed in as fiducial markers. We imaged the model in situ with loading at our MUVIS X-ray Imaging Centre in Southampton, and we used digital volume correlation to show how different sockets can produce different strain distributions and how the strain inside the limb doesn't necessarily correspond to the pressure on the limb's surface. So to conclude the talk, where next? Several research teams have been considering for a decade how optimization might be useful to improve socket design, and most commonly they consider topology optimization to adjust the socket thickness or cutout shapes. We've undertaken a small study using a genetic algorithm with our finite element population model to perform multi-objective optimization to see how socket design might vary for different fitness functions. As plotted on this Pareto plot, we can either offload by priority the vulnerable distal tip of the limb with fitness function 1, or we can offload the proximal bony prominences with fitness function 2. And we showed how these would provide a range of different feasible socket designs along the red Pareto front, and how this might vary for different synthetic test participants using our statistical model. There are also considerable efforts which are building in the community now to look at how machine learning from expert clinical practice might be used to support socket design. Recent work from the EU Socket Sense project has demonstrated using fuzzy logic to merge interface pressure measurements with design input from panels of clinicians. And we're currently working on supervised machine learning to interpret statistical design models of patient-reported outcome measures. I would advocate great care in this area though, having been able to talk to the experts. Optimization and machine learning can be used as a black box and have been proposed by some as an automated design method, and I would suggest this is rather risky. For the reasons I mentioned earlier, clinical translation will depend both on implementing these technologies safely and having the experts on board, demonstrating how the technology will support them in understanding and sharing their experience with trainee colleagues, and letting them focus on the high value added parts of their job, so fine-tuning the design to a particular user, while these technology tools could be left to do the more basic and crude but time-consuming tasks, perhaps providing a new generation of statistically and outcome-informed smart socket templates. So with that, I would like to thank the ESB again very much indeed for allowing me to give you this talk, and to you for watching it. And I'd be delighted to discuss any of the contents with you at the meeting virtually, or you can contact me here and I'd be very happy to talk to you. I need to thank some wonderful colleagues and our funders, and especially our participants who volunteered their time to support the research. Thank you very much.